Alright, we got a bit of work to do for statistics. We got a bit of catching up to do from the first quarter being, wasting our time with the project when none of the teachers were going to, well, say none, half the teachers were going to hand in the forms, and the ones who did, few of them decided not to fill them out completely because they don't understand how data collection works. So this is the frustration of statistics, really, when it comes to collecting data. It's always the worst part. So, and of course, from the second half of a few weeks being taken out to get the yearbook completed, which again, we're both all glad that that's done. So we're going to do chapter 7, 8, 9, 10, and 11. So we got a bit of work to do. Now, fortunately, is chapter 7 we get done today. It's really the basic chapter. Some of these are going to be really quick, and we're going to have a kind of video lesson of the PowerPoint, followed by some work done on R. So those are going to have to be separate because this is on my tablet, and until I can get the writing utensil that I have coming in the mail for my computer, it's all going to be two separate videos. So that should be coming in on Wednesday, so we'll see if I can get all that to work. So all this is new to me, making these videos, so we'll go ahead and get started. Now for chapter 7, it's 5 sections. We're only going to do the first 3. So the first section is properties of normal distribution. So we're going to look at uniform probability distribution. Not so much. It's just a thing that we'll talk about. We're going to look at graph a normal curve, state the properties of a normal curve, and explain the role of area, normal density function, and describe the relationship between normal random variable and standard normal random variable. So a bit to do for this first section. So let's first look at uniform distribution. Now suppose the United States Parcel Service is supposed to deliver a package to your front door and the arrival time is somewhere between 10 and 11 a.m. Let the random variable x represent the time from 10 a.m. When the delivery is supposed to take place. The delivery could be at 10 a.m. where x is 0 or 11 a.m. where x is 60, with all 1 minute intervals of time in between x equals 0 and x equals 60. So that's to say that your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. So this is what it's going to look like. Okay, so there's the probability density function. Here, the big thing about this that we want to look at is the total area under the graph. So the total area under the graph of the equation over all possible values must equal 1. So that's the big thing, that the area equals 1. Okay, height of the graph of the equation must be greater than or equal to 0. This is basically, if you remember your rules of probability, your probability must be greater than 0. Okay, and the sum of all the probabilities, so the total area, must equal 1. All right. So this follows along with your probability rules. So here's the graph of that density function when it talks about delivering each minute. So 1, 2, 3, all the way down to 60 has a height of 1 out of 60. So to find the area of this length here is 60. This height here is 1 out of 60. So the area is, again, just using rectangle, base times height. 1 out of 60 times 60 is 1. So the area is 1. This is a uniform density function because it basically forms a rectangle where every value on your x-axis has the same amount of probability of occurring. All right, and that's really it for normal density functions, or uniform density functions. We're going to go into more normal density functions, so I'm going to skip on down because I'm not going to really ask you really any questions about uniform density functions. They rarely exist. So this is a normal curve. This, if you remember making histograms and you have a symmetric histogram, this is what forms from the histogram. This is basically drawn over the histogram. to kind of give you an idea of where that curve comes from. It's drawn over a histogram, and it's an estimation of the actual data that we're going to be dealing with. Now again, it is an estimation, and that's what we're going to be dealing with pretty much from now on, is a lot of estimations, but they are informed estimations. It's like the title of your book, Informed Decisions. They're really, really thought out estimations. Okay, so this is where the normal density curve comes from. It is a curve drawn over a histogram. All right, I don't really think, and again, for those who took statistics, okay, inflection points. Yay! Sorry, those who took calculus, there's your inflection points. All right. The very center, the big thing about this is this, for your normal density curve, one thing is the whole thing must be above 0. So none of it goes below the x-axis. So here's the x-axis. None of it goes below the x-axis. It looks like it's going to go, but it doesn't really ever touch the x-axis. The center of it, the peak of it, okay, if we have symmetric data, again, we're going to assume symmetry quite a bit here. So if we have symmetric data, then the center, this is your mean, median, and mode. Okay? But we're going to pretty much just use mean here. So if you remember mu, your symbol mu, that is your mean. Alright? And then as we go from the center, we either increase by standard deviation, so we're adding sigma, your standard deviation. Now again, these are population mean, so population mean and population standard deviation. All right. So this is your normal probability. As we increase, we add sigma. As we go to the left, we subtract sigma. All right, but the very center is your mean. Feel free to pause at any point in time. I'm going to move on because I can't know if you're busy writing all this down or not, or just paying attention because you had the video and you have access to the video. So feel free to pause at any point in time if you're writing down these notes. I'm going to move on because I'm in my living room and my kids are going to wake up at any point in time. So, all right. So we can have various types. This here just shows you kind of the various types of normal density functions, normal probability functions, to where we could have our mean at 0, okay, or we can have our mean at 3, okay, with a standard deviation of 1 each time, okay, or we can have a mean of 0 with a standard deviation of 1, or a mean of 0 with a standard deviation of 2, okay. Now, the smaller your standard deviation, the more condensed and kind of taller your curve will be. The higher the standard deviation, the more spread out it will be. Again, remember, standard deviation is your measure of spread. Okay. All right, properties of a normal curve. Here they are. All right, it is symmetric. Again, we're going to assume symmetry quite a bit. And the center is the mean, mu. All right, because mean, median, mode are all equal, there's a single peak. Highest point occurs at mu. It has inflection points at mu minus sigma, mu plus sigma. That's not really important, okay? You don't really care about that. This is important. The area under the curve is 1. That way we can use it to find probability. Basically, what we're going to do to find probability is find the area under the curve at certain points. Okay, so if the area under the curve at certain points, let's say you're taking the ACT, and you know what the mean and the standard deviation was for the ACT, and you want to know what's the probability of scoring better than a 27, we can find that by using this curve here. So, area under the curve to the right of mu equals 1/2, and the area to the left equals 1/2. Yeah. X increases without bound, gets larger and larger, and the graph approaches but never reaches the horizontal axis, which is kind of mentioned earlier. It never quite reaches the horizontal axis. It never goes below the horizontal axis. Okay, and then we have the empirical rule. So we're going to talk about the empirical rule. It's best to really, when we talk about it, just know it's often called the 68, 95, and 99.7 rule. Okay, the empirical rule is an approximation. Okay, it is a well thought out approximation, but it's still just approximation. Okay, so this is something you may, if you have, you have access to PowerPoint, I would just print this out. Okay, I don't know why I just circled that part, but you need the whole thing. I would print this out because it's really, really handy. There's something you want to know over here. This kind of missing here is what goes beyond, because this is just the shaded areas. So this area between mu and mu minus sigma is 34% of the whole thing. So if the whole thing adds up to 1, that's 0.34. From mu to mu plus sigma, same thing. This is 0.34 of the area. Now, what's missing here is what's beyond 3 standard deviations. Let me exit out of here so I can start again, because I can't get rid of this drawing. All right. So what's missing here, the fact that this is 1 sigma, this is 2 sigma, and this is 3 sigma, is what's beyond 3 sigma, and beyond 3 sigma is 0.15% of the data. There's still stuff, but it just goes on, and it's so insignificant that we really tend to not worry about it too much. Same thing over here. What goes beyond negative 3 sigma is 0.15% of the data. So this is negative sigma, negative 1 sigma, negative 2 sigma, and negative 3 sigma. And this gives you your empirical rule. It says from the mean, from the center, 1 standard deviation away, which means plus sigma or minus sigma, 68% of the data. All right. So just to give this context, let's say the ACT had a mean of 21.6. I don't know what the actual mean is, but that's a good number right there. And the standard deviation of, let's say, 2.7. Okay. That means starting at the center, 21.6, if we add 2.7 up, so adding 2.7, 20, so adding 2, 3, 4.3, 2.7 would be 27, 2.7, 29.7. Subtracting 2.7, so 19, 18.9. And then subtract 2 points to 16.2, and then 13.5. So, what this says is 68% of those who took this ACT scored between an 18.9 and a 24.3. So 68% of the people who took the test scored between these two, or this interval. Okay. 95% of the people who took the test scored between a 16.2 and a 27. Somewhere in this interval, holds 95% of all the test scores. And the 99.7% is equal to has scored between a 13.5, which I don't even know is possible, and a 29.7. So that is an example of how the empirical rule works. We are going to be given a mean and a sigma. You have to be given a mean and a standard deviation. There's no choice on that. All right, they're going to ask you what percent falls in between two specific numbers. So really, you just complete the chart here. You start with the mean, add sigma, and then subtract sigma, and then you have your values to find your percentages. Now they may ask, what percent scored above a 27? So that means going from the 27 here and on, I would add up just these two right here. Okay, so if adding those together, that's 2.5% scored above a 27, which means 97.5% scored below. Right. Now, if you ever remember, if you get back your ACT data, usually they give you percentile ranks and stuff like this, and this is really what it's based on. Okay, you're in the top 99%. That means you scored better than 99% of the people who took that specific test, and this is how they find that information because it is fairly symmetrical. Once you get enough data, once you get plenty of data, lots and lots of data, like the ACT has, because everybody's taking it. It becomes fairly symmetrical. It becomes a fairly normal distribution. And they have a way to find the mean and the standard deviation because they have all the data. So it is very possible for them to find that. All right. So hopefully I've done this well enough. Again, feel free to ask questions. If you ever have questions, just go to the comment section under, either email me or go to the comment section under the Google Classroom. There should be a way to comment on any of the homework. And honestly, I'd rather you go there because everybody, I think a lot of people get the information that there's a comment there. So anybody can see the comment and maybe answer it if I don't get to it quickly enough. So yeah, I would comment there. Mainly also because if you have that question, probably other people have that question too. The other two people in the class. All right, we're moving on. Explain the role of area. So we kind of did that a second ago. The area is used to find probability. Okay. So data next slide represents the heights and inches of random sample of 52-year-old males. All right, draw a histogram of data using the lower class limit and the first class equal to 31.5 and a class with the 1. Do you think the interval that the variable height of 2-year-old males is normally distributed? Now, I'm not going to do this. Okay, there's the data. I'm not going to make you do this at all either, so don't stress this. All right, but so here is the information. Now, does this look fairly normal? Yeah, that's fairly normal. So yeah, centered around what, 35, 36? There we go. So next slide, we have normal density curve drawn over the histogram. How does the area of the rectangle correspond to the height between So I'm going to move on. This is just kind of silly. I explained all this already, so all right. We can say the area, the portion of the population with the character described by the interval or values. The probability the random selected individual from the population will have the characters described by the interval. So again, we are used to find proportion, probability, and even percent. Like we said, 95% or 92.5% scored above a 27 on the ACT. So we find proportion, probability, and percent using the normal curve. So I'm going to move on out of here. Again, I'm not going to have you draw these and do all this stuff. Okay, that's just kind of a waste of time. Okay. All right. Okay. Give me a second. Sorry, I'm going to pause here. All right, sorry about that. My coffee was ready, so I'm going to take some coffee now. I don't know if you can believe that, but I'd actually functioned for a bit without coffee. So, all right. So here we're going to describe the relationship between the normal random variable, okay, and the standard normal random variable, okay. So this normal random variable is right here. This is called your z-score. So z-score, also sometimes called the test statistic. Okay, now there's a couple of versions of test statistics. There's Z and there's T, and we'll talk about T later on. So, all right. So, Z, what Z does is this allows us to standardize. Again, standardize any normal random variable. So this is your normal random variable. X is your normal random variable. Z-score allows us to standardize it. So like we said with the ACT score, usually we can't, there's words here I'm trying to use and it's early morning. Okay. With standardizing a normal random variable, we can take any data set, such as ACT scores, okay, and then weight of infant children, well, infants, so because infant would be children. And we can find probability on either one of these data. So we could also find average salary. Okay, and all of these are different types of data, but we can standardize them using z-scores, using this formula, so we can find probability using the same method, using your normal distribution curve. Okay, so it doesn't matter what the data is, we use this to standardize it to the normal curve. That is what standardizing normal random variable does. Okay, so this is really what we're going to focus on more today than anything else. This is where your homework is going to really come in. It's just this part right here. So the weights of giraffes are approximately normal, distributed with a mean of 2,200 pounds, a standard deviation of 200. Draw a graph. I'm not going to draw a graph, but I'm going to do this. I'm going to find the z-scores of these two. Okay, so again, z is equal to x minus mu over sigma. In this case, mu and sigma are given, just straight out given to us. And this is what we'll call x1 and x2, since we have two z-scores. Okay, and we will find basically the z-scores for just these two. All right, so we have a z1, so that's going to use your x1 value, 2,000 minus 2,200 over 200. That just gives you -1. And then z2 is to 2,300 minus 2,200 over 200, and that gives you a half, 0.5. Now, usually your z-scores, rule for z-scores, and that's not the c scores, is you always go to 100th place. You round to the 100th place. Always. The z-scores will always round to the 100th place. Okay, now this we didn't have to because this is an easy question, and it gave us nice whole answers. Well, mostly whole. All right. So most of 7.1, I'm just going to have you practicing the z-score and maybe answering a few questions about normal distribution and the empirical rule. Okay, so that's what I'm going to do for you guys. Is basically 7.1 is going to be empirical rule and z-scores. Okay. 7.2 is we're going to be using those z-scores to find area. Okay. And then we're going to find z-scores based on a given area. Now here, what we're going to do is we are definitely going to use R for these. Now 7.1, I'm probably not going to use a lot of R, but for 7.2, we are going to start into R. Now I'm going to have to do, again, a separate video of that later. I'm just going to kind of go over all this right now, and then you're going to have a separate video about how this applies on R. Okay, so this is our normal density curve, so we're good there. So properties of the standard normal curve. Yeah, I'm not going to waste your time with this. The big thing is area in the curve is 1. That's so we can use this to find probability. You could do a lot. It is symmetric, mean. This is really the same as the property of the normal density curve back in the first section. Just everything is centered around. Try to go backwards now. Everything's centered around 0 instead of around mu. They just assume, basically, because you standardize it, the distance mean is from the mean is 0. So that's why it's always centered around 0. All right. And there's your empirical rule here at play. All right. So find the area under the standard normal curve. Now here, we're going to have 2 ways to do this, or 3 ways. You're going to find the area to the right. No, this is not right. This is left. Area to the left. Area to the right. And then area between. All right. So we have 3 different options here. We're going to have 3 different ways to do this on R. Okay, really, it's not going to be a big deal. Basically, right is always 1 minus the left. And that's pretty much what we're going to put on R anyway. It's just 1 minus the left. Between, it's back when we had 2 z-scores. Okay, so it's basically what you're going to do is find area to the left on both. On both z-scores. Z1, we'll say Z1 and Z2. And subtract. Now, since probability must be positive, it's going to be bigger minus smaller. All right, so, okay, now, see here we don't even have to find the z-score. They give us the z-score. Now, there's a couple ways to do this. We're going to use R, okay? We are going to use R to do this. We're going to use R to find the z-score. Again, that's just a calculation. You could do that on your calculator, or you can have R do it for you. Some of the cases we are going to use actual raw data, so you're going to be using the mean and standard deviation of raw data, but often you're going to be given sigma anyway, so you don't have to worry about finding, well, sigma, not z. So if you're ever given z, then it's really easy just to plug it in on R. Here, they're going to show you this chart here, which I'm just going to ignore because we do not need this chart, okay? I'm going to show you how to do this on R. Okay, so that's just the answer. Again, on R, we actually should get a more precise answer because R doesn't round it. Okay, we can probably set it up to round it, but that's the way it's going to be. All right, and like I said, area under the normal curve to the right is 1 minus area to the left. That we already mentioned that right there. So here it'll kind of is spelled out for you in actual legible writing. So moving on. All right, again, finding z, it's just going to use the chart, so I'm going to have to do this on R. I'm going to kind of go through all this back on R. All right, in the area between, you find the area to the left on both, and then subtract those areas. Again, we're going to do this on R. So this might be good to have, so give you an idea. That area to the left, we're good. Area to the right is 1 minus area to the left. And area between is you find area to the left for Z1 and Z2 and subtract. Don't subtract Z1 and Z2, subtract their areas. So find the areas first, subtract the areas. And that's how you find the area between. All right. Again, I think we're just going to do most of this on R. So finding z-score, we should be able to find specific z-scores for areas as well. So a lot of this is going to be on R. I'm just going to move on. Okay, we'll talk about this in a second. I'm going to pause again real quick. So what I'm going to do for these is I'm going to do these on the computer, but I can't write on the computer, so you have to see everything on R. So I'm basically going to go back to the PowerPoint through this. So you see the PowerPoint open, you're going to see R open, and I'm going to go through all of this right here, basically all 7.2, going all the way back here. So all of this is going to be done on R. So I'm going to basically pop up the PowerPoint on R and show you how to do this. Instead of just running through this right here and making you dizzy through this video. So, anything else? I'm just checking to see if there's anything else we need before we put this on R. Oh, these are the symbols we'd like to use when finding probability. Okay, so probability of z being between two values. This greater than, this is area to the right. So usually instead of doing greater than, we do 1 minus the probability that z is less than a, because this is area to the left. All right. So these are just how we note. This is a notation for probability. So if you see find this, or find that, or find this, that's what it means. This greater than means area to the right, less than means area to the left. Very important you know that, okay? Because anytime you find area to the right, you do 1 minus area to the left. All right, again, we'll do this on R. This is finding area to the left of this value, area to the right of that value, and area between these two. So we'll do that on R. What are you doing? Get back over here. All right. Again, this is other stuff we're going to do on R, so I may pause here and just, yeah, do this all on R. So that's what I'm going to do. I'll go ahead and get this set up on there, and then I'm going to have this on my computer and R open. I'm going to post both of these videos together. So really, I may, I'll just post both these videos together. Watch this video first. Of course, this is the end of the video, so what am I saying? Watch this one first. I'll put a note to watch this video first, and then watch the R video second.